Dear friends, welcome to the lecture of the Riemann Integral. We are studying fundamental theorems of calculus. In our last lecture, we have studied theorem number 5, which is first fundamental theorem of calculus. I have written the statement of that theorem for reference again, and we will now study in this lecture theorem number 6. Now, what is the difference in theorem 5 and theorem 6? That we shall see first. This is the theorem we have proved in our earlier lecture, which is first fundamental theorem. If f is continuous on the closed bounded interval a to b, and if f of x, capital F of x is equal to integral of small f from a to x, then the derivative of this capital F of x is equal to small f of x. This is the theorem that we have proved. Now, we see what is theorem number 6. If f is Riemann integrable over the closed bounded interval a b, and if f of x is equal to integral a to a, capital F of x is equal to integral a to x, small f of t dt, x lies in the interval a to b, and if f is continuous at x naught, belongs to the closed interval a to b, then f dash at x naught is equal to f of x naught. You see both these statements. The first change is here f is continuous on the interval a to b, closed interval a to b, and here it is given that f is Riemann integrable on the interval a to b. Now, what is the difference in these two? F is continuous on the closed interval a to b, and f is Riemann integrable on the interval a to b. Here f is continuous on the interval means f is continuous at every point in the interval a to b, and f is Riemann integrable over the interval a to b, we know is f is continuous at almost every point in the interval a to b. That is the difference. There every point, and here almost every point. That means there may be a few exceptions. And what is the meaning of almost every point? Means the set of points at which f is not continuous is of measure 0. That means there may be a countable number of points at which f may not be continuous, but here f must be continuous at every point. That is the difference in the first condition, and therefore this theorem is the improvement of that theorem. That is the general case is considered here. Here the condition is strong, here the condition, this condition is somewhat weak. And second thing is, this condition is the same. Capital F of x is equal to integral a to x f of t dt, and x is in the interval, that is the same. Then and if f is continuous at x naught, we have written f is almost continuous almost every point in this interval, and we consider the point of continuity. F is continuous at x naught in this interval, x naught belongs to this interval, then the same result holds for x naught. F dash of x naught is equal to small f of x naught. So, this is the difference in the theorem number 5 and theorem number 6. Here it is considered for all points, continuity at every point, and here continuity at almost every point. And we have considered a particular point x naught, function f is continuous at x naught, and at that point f dash of capital F dash of x naught means derivative of capital F at x naught is equal to the value of small f at x naught. So, that is the difference. Here it holds for every point, and here it is a particular point only, x naught, at point x naught only. That is the difference in the theorem number 5 and theorem number 6. Now, we shall prove this theorem 6. First, we shall assume we shall take h value. Let h is greater than 0, and let we consider the interval IH as the closed bounded interval x naught to x naught plus h. We will consider this interval, and you see this is in that will be contained in a to b, and that means we are considering like this, that is the interval a to b, and we will suppose x naught is somewhere here and h is positive, means x naught plus h will be like this. So, this interval is contained in the the interval, original interval given, that is a to b. Now we shall consider the oscillation of the function f in this interval, the function small f. We have oscillation of small f over this interval IH is, by definition, this is the difference in maximum value of the function over that interval capital M. We have denoted the maximum value by capital M minus minimum value of the function over that interval IH. So, this is what we have by definition. And now we shall consider, let x be any point in this interval a to b. Let, or in general we can consider t. T belongs to the interval a to b, or in that interval we will consider it as from x naught to x naught plus h. Then we have the relation we will write as the value of function at x naught minus oscillation of function over the interval IH. IH is this interval, and that will be less than or equal to f of t is less than value of the function at t, and that is less than or equal to f of x naught plus oscillation of f over h IH. So, this is the relation that we will have. Now, how this is so? See, suppose the interval we will consider figure to understand how it can be. What oscillation means, the difference in maximum and minimum value, and therefore we are subtracting oscillation from this point. So, this will be a lower value, and we are adding oscillation at the same point f of x naught. So, every value of the function in this interval will be between these two values, or we may see the figure can be considered like this. Suppose this is the interval a to b, and we will have x naught to x naught plus h. Suppose from this point, I shall consider the figure like this, and let this be x naught plus h and this be x naught. So, what is the oscillation of the function? This is the graph of the function which is y is equal to f of x, and oscillate the max. This is the maximum value, you see, function's maximum value, and this is the function's minimum value. This is m and small m, and what we have is f of x naught. F of x naught is this value. This is f of x naught. So, we are subtracting the oscillation of the function from this value f of x naught. So, what is the difference of m and small m? This will be the difference. This is actually the oscillation. This will be the oscillation. Capital M minus small m is the oscillation. And if we subtract this oscillation from this f of x naught, we will get a value here, somewhere here. We are subtracting this, and therefore, the left side will have only this value. This is the left side here. And f of t means any value of in the interval function's value at in the interval x naught to x naught plus h, means any value in this range, small m to capital M. And what is the right side? Right side is f of x naught plus oscillation. So, this is f of x naught, and we add this oscillation to this. So, therefore, this oscillation is added, and this will be the right side. So, that means the extreme left side is this value, and the extreme right side is, we have added the oscillation to this value. This is a fixed value, and this oscillation is added. This is the fixed value, this oscillation is subtracted here. And then the any value of the function certainly will lie between these two. So, these are the values of the function between this value and that, any value of the function, that is f of t, and that is the justification for this step. Now, what we should do further is we integrate this throughout, that means integrate each. So, we have, and this is by corollary, The integration of this will be less than or equal to integration of this second, and is less than or equal to integration of the third expression. So, integrating this we get integrating and using this, this is corollary 1 by corollary 1 we have. Now, see, when we integrate in the interval x naught to x naught plus h, so integration of this will be x naught to x naught plus h, and this is f of x naught minus oscillation of f over the interval I h, and with respect to t we are integrating. So, this is the integration of first term is less than or equal to integration x naught to x naught plus h f of t dt, and that is less than or equal to. So, I shall write here that is less than or equal to, this is the right side, extreme right, that is integral x naught to x naught plus h f of x naught plus oscillation of f over I h dt. So, this we will put in bracket. Now, in this see, this expression is constant, because here that this is a fixed value at x naught. So, we have seen this is f of x naught and this is the oscillation. So, actually this is the value only in this part. So, or this much is the value of this expression, and therefore, it is a constant. So, we can write the constant outside the integral by theorem number 4, and then we will left with integral x naught to x naught plus h dt. And we know that that integral is the length of the interval, that is h. We have used this type of result in theorem number 5 also, and further this implies, so therefore, we can write this term f of x naught minus oscillation of f over I h, and this is multiplied by h, because integration of x naught to x naught plus h dt is h. So, that is h, and is less than or equal to the middle integral we will keep as it is, x naught to x naught plus h f of t dt. And similarly, the integral on right we can consider this as this is a constant. So, it will remain the same, f of x naught plus oscillation of f over I h, and this is multiplied by h, since integration of x naught to x naught plus h of 1 dt is equal to h. We have used this integral of this over dt is h, and now we will divide this expression by h. So, dividing by h we will get see this h cancels, and this expression remains as f of x naught minus oscillation of f over I h is less than or equal to, and we have to divide this by h, or we can write 1 by h integral x naught to x naught plus h f of t dt, and that is less than or equal to the extreme right term is f of x naught plus oscillation of f over I h. So, this is the expression that we shall get. Now, we shall suppose this as this relation or statement as 1, and now we can use the expression for this function. By hypothesis, it is given capital F of x is the integral of f of t. So, by hypothesis, capital F of x is equal to integral a to x f of t dt, and from this we can write. So, therefore, capital F of x plus x naught plus h we will consider x naught plus h. X is to be replaced by x naught plus h, and that will be equal to integral a to x naught plus h. You see, here x is we are replacing by x naught plus h, and therefore on the right also we replace x by x naught plus h, f of t dt. And what will be f of x naught? And f of x naught is x is to be replaced by x naught, f of t dt. Now we shall subtract these two, and that gives, so the subtraction will give as f of x naught plus h minus f of x naught, and that is equal to integral a to this integral, above integral subtracted, we have to subtract the integral below, f of t dt minus integral a to x naught f of t dt. And now we can split this integral in two parts, a to x naught and then x naught to x naught plus h. So that integral a to x naught will cancel with this integral, and simply this becomes, or this remains as integral x naught to x naught plus h. We have done this same steps in the earlier theorem, theorem number 5. So we can use here theorem 3, that integral a to b can be written as integral a to c plus integral c to b, where c is the point in a to b. And here this can be written as, see the points are like this. So here is a, x naught plus h, or before that it will be x naught, and we have assumed x naught, h is positive, and then b. So the integral a to x naught plus h is integral a to x naught plus integral x naught to x naught plus h, and therefore this is two parts, and this first part cancels with this last part, third part, and therefore only the integral between x naught to x naught plus h remains. So this is what is f of x naught plus h minus f of x naught, and we can use this value in this second relation, integral x naught to x naught plus h f of t dt, and that we will use here, and that will be 1 by h term is there. So from 1 we have, so I shall write here, therefore from 1 we have, see the left side is as it is, f of x naught minus oscillation of f over I h is less than or equal to 1 by h into this integral, means 1 by h into this, or that will be f of x naught plus h minus f of x naught divided by h, and that is less than or equal to the right side. So that is less than or equal to f of x naught plus oscillation of f over I h. So this is what we have, or you may suppose this as second, and we can write from 1 and 2. We have used 1 and 2. So this is the relation, and we shall now suppose this as 3. And now we shall use the fact that f is continuous. See here, f is continuous at x naught belongs to the interval a to b. By hypothesis, it is given in the theorem, and therefore we write by hypothesis f is continuous. F is continuous at x naught. X naught belongs to the interval a to b, and therefore oscillation of f over I h will be 0. If a function is continuous, or we can write first oscillation of f at x naught. Oscillation of f at x naught is equal to 0. If the function is continuous, its oscillation continuous at a point, then its oscillation at that point is 0. The maximum value of the function at that point and the minimum value of the function at that point must be equal if the function is continuous, and in that case the oscillation becomes 0, and therefore oscillation of see the interval we have considered as x naught to x naught plus h, and therefore as h tends to 0, oscillation of f, or we can write limit h tends to 0, oscillation of f over the interval IH, or first we should consider the h tends to 0. What is the interval x naught to x naught plus h, x naught plus h will be the same point as x naught, or that will be a single point, and that is limit, this is IH. So, limit h tends to 0 of IH will be a single point, and that gives the oscillation of f at IH will be equal to 0 as h tends to 0. So, instead of this we write the oscillation of f on the interval IH is equal to 0. So, that means the oscillation of f at IH when h is the point is x naught, means the interval becomes single point x naught plus h. This will tend to x naught point when h is tending towards 0. So, therefore, oscillation as h tends to 0, oscillation of this is IH, and therefore, oscillation at x naught is 0, means oscillation of f at IH it becomes 0. And now, we shall take the limit of this as h tends to 0. So, this is IH, and in the result 3 we will take the limit as h tends to 0 throughout and use this result. So, taking limit as h tends to 0, as h tends to 0 in 3 and using this result, we get or using this result, yes, we will use this result, we get. Now, see what we will get. This when we take the limit, this is a fixed value, so it will remain the same, and that will be f of x naught. And what is this value? When we take the limit, it is 0, f of x naught minus 0, and is less than or equal to limit h tends to 0. I will write limit for this, f of x naught plus h minus f of x naught divided by h, and that is less than or equal to, here this value is becoming 0. So, f of x naught, and thus see, actually we have written the direct value of this limit of this as 0, and but for the middle we have written limit h tends to 0. What is the middle term? That is, by definition, it is a derivative of capital F at x naught, and thus we have this is f of x naught is less than or equal to capital F of x naught, derivative of capital F of capital F at x naught, and that is less than or equal to f of x naught. Now, what this implies? This value lies between these two terms, means it must be equal to the same. So, all must be equal, and hence thus we have f dash of x naught, capital F dash of x naught is equal to small f of x naught, and this x naught is in the interval a to b. X naught belongs to the interval a b. So, or it is a closed interval a b. So, f is continuous at this interval x naught a to b, and therefore, we have used this fact that oscillation of f at x naught is 0, and taking limit we get the result, and this proves the theorem. This is what we wanted to prove. So, this proves the theorem. So, thus we have proved a theorem which is theorem number 6. Now, we shall prove a short theorem which is theorem number 7 we shall consider, and it is easy to prove, but it is important to prove the theorem or to use it in the second fundamental theorem. So, if f is Riemann integrable over, or we can write if f dash of x, the theorem is if f dash of x is equal to 0 for x is between a to b, then f of x is constant on the interval a to b. If f dash of x means derivative of f is 0 in the entire interval a to b, x in the interval a to b, closed interval a to b, then f of x is constant on the interval a to b. That can be written as constant means f of x is equal to c. A is less than or equal to x is less than or equal to b for some c is real number, for some c belongs to R, real number. So, this is the theorem which is simple, and we know if the derivative is 0, the function is constant. That is the meaning of the theorem, but we shall prove it. And it is given the function is Riemann integrable, and it is its derivative exists at every point from a to b, and therefore the derivative exists means the function is also differentiable. Since f of x is differentiable on the closed interval a to b, f of x is continuous. It is continuous on the same interval, because differentiability implies continuity. That is the result we have studied earlier, and therefore f of x becomes continuous on the closed interval a to b, and therefore we can consider f of x is continuous on the interval a to x, where we can take x between a strictly less than x is less than or equal to b. Take a x point between a and b and restrict the interval a to x. A to x is contained in a to b. It is continuous in the whole interval a to b, therefore it is continuous in the interval a to x, because x lies between a and b. So, and here we can apply the law of mean or the mean value theorem. So, by the mean value theorem or by the law of mean, we have there exists C belongs to the open interval a to b, such that this is the law of mean, such that f dash of c, derivative of f at c is equal to, this is small c, derivative of f at c is equal to f of x, this interval f of x minus f of a divided by x minus a. This is law of mean. Actually it is Lagrange's mean value theorem. And now what we have, f dash of c is by hypothesis is 0, because f dash of x is 0 at every point from a to b, but by hypothesis f dash of c is equal to 0, and therefore we have 0 is equal to f of x minus f of a divided by x minus a. This implies the numerator must be 0, and here x minus a is not 0, because a is less than x. So, therefore, this is not 0, x minus a is not 0, and this implies f of x minus f a is 0, or that is f of x is equal to f a. F of x is equal to f a, and a lies this x lies in the interval a to b. So, a is less than x is less than or equal to b. So, that is the relation that we have, and therefore, f of x is equal to c for where c is equal to this, c is equal to f a, that is a constant or a real number. So, we can take this f of a, it is a fixed value, and therefore, we can take that value as c and capital C, and therefore, this the function is constant. F of x is equal to c means function is constant. So, this is the result. When the derivative is 0, the function is constant. We have used Lagrange mean value theorem to prove the theorem. So, thus we have proved in this lecture two theorems, theorem 6 and 7. The remaining part we will continue in our next lecture. Thank you for watching the lecture.